Do you remember the future? You first experienced it when you were younger, much younger. It came to life in experiences imagined, experiences created to entertain and foreshadow what will be. You saw universal communications driven by pure imagination.
Hallo Stefan, guten Morgen, wie geht es dir?
Good morning, Stefan. How are you?
I'm well, Christian. Did you receive my proposal?
Mir geht es gut. Haben Sie meinen Vorschlag erhalten?
A world in which we pushed ourselves to fantastic new limits of exploration. Machines with the ability to make us whole again. Advanced devices that gave us the power to see clearer and heal faster. Robots created to help us reach farther and stay safer. And you saw vehicles that drove humans rather than the other way around. When you were younger, much younger, these visions awed and inspired you. Today, through the power of deep learning, they talk to you.
That would be good.
And heal you. And move you. Do you remember the future? Look around you. It's here.
Ladies and gentlemen, please welcome Nvidia co-founder and CEO, Jensen Huang.
Good morning, welcome to GTC 2015. Welcome to Silicon Valley. GTC is about developers. GTC is where we share what we've learned, we share ideas, we're inspired by each other's groundbreaking work, and we dream about the future. We got lots to talk to you guys about this year. We have a great show for you. GTC is about you. Let's get started. I'm going to talk about 4 things today. 4 announcements. The first, and every GTC needs it, is a new GPU. This year I'm going to talk about a new GPU and deep learning. I'm going to talk about a very fast box and deep learning. I'm going to talk about our roadmap and show you the next click of the exciting work that we're doing at Nvidia and deep learning. And I'm going to talk to you about self-driving cars as it relates to deep learning. So I don't know if you've noticed a trend, a thread, but we're going to talk a lot about deep learning. We have a lot to talk to you about. This topic of deep learning is probably one of the most exciting things that's happening in the computer industry. Arguably as exciting as the invention of the internet. And I think by the end of the show, by the end of the event, you're going to realize the amazing work that people are doing in this field, its amazing results already, and its amazing future. The potential of this technology, the potential of this work, and its implications to all of the industries, and all fields of science. Amazing applications. The possibilities are really just endless. And so I want to dedicate my entire talk on this topic. And that's surely not enough time. And in fact, you're going to see a lot of other talks dedicated to this topic. And I think that we're going to talk about this for the next decade. For many of you, you're already deep in this field. For many of you, you're getting an introduction to this field, and hopefully all of you will be inspired by the work. But before we start, let's talk about last year. We had an amazing year last year. A lot of exciting developments. Of course, GeForce. GeForce is the #1 PC gaming platform in the world. The PC gaming market is the largest of a massive $100 billion gaming market. It is still growing. The production of games increasing all the time. The type of genres like MOBA, massive online, battle arena, and of course VR, making a huge difference in the future of gaming. Gaming is also important to all of us because not only because it's fun, but because it's such a large industry and because it's so technically challenging, it is the fuel of our R&D. A couple of weeks ago, we announced Nvidia's first living room entertainment product, the Nvidia Shield console. We want to do with the Shield smart TV device, we want to do for the television experience what smartphones has done for mobile. We believe that the television is finally able to be revolutionized. We have the fundamental technologies now to enable a whole new type of experience for all of you. Shield was designed with a Tegra X1, the fastest, most powerful mobile chip in the world. It's snappy, it's 4K, of course, because it's built by Nvidia. It is also made to game. We're really excited about Shield. Cars. A car is essentially software, computers on wheels. What's happening in, of course, what happened in mobile industry with the smartphone is now happening also in the car industry. The type of experiences you're going to see in the near future are really quite inspiring. The days of dials, knobs, buttons are gone. The future of your car is going to be digital displays, touch, gaze, voice, gesture, all kinds of amazing ways to interact with the car. The car is going to be one delightful computer rolling down the streets. It'll also be smart. And when we say smart, of course, in the context of smart in this conference, is related to deep learning. And so today we're going to talk also about the implications of deep learning and our perspective on how deep learning could affect the future of car designs. We had a record year in our car business, doubled year over year. We had a record year in our enterprise business. Enterprise graphics continues to be very exciting. This morning I read a news article that said the work that we're doing, the Nvidia Grid virtual GPU, is like nitrogen to VDI. Nitrogen in a car, of course, turbocharges it. In the case of VDI, now with grid accelerated VDI, there's no reason why anyone should have a bad VDI experience anymore. This business is really doing well. Last year, we saw 1,800 trials, deployments, pilots, and a growth about 100% year over year. This is going to be a very exciting area of growth. For the 5th consecutive year, Nvidia Quadro was involved in the creation of the Oscar-winning movies in the best special effects. It is now in the process of helping create the next Star Wars. You guys can imagine how exciting that is. I'm nearly out of my body excited about it. We can't wait. I'll create any technology to help them make Star Wars faster. Last year, we also had a record year in Tesla. Tesla is our supercomputing platform. Our country, the Department of Energy, selected Tesla with NVLink to power the world's next 2 fastest supercomputers. There are supercomputers being built everywhere. Baidu recently announced, and this is probably Andrew Ng's lab, announced that they were building a supercomputer for artificial intelligence work. There's supercomputers now being built in internet service providers, consumer web services companies all over the world. The implications of supercomputing, high-performance computing, in the future internet services is pretty exciting. And in fact, it led to one of the greatest achievements of this year. For the first time in history, a computer visual recognition system was able to beat a human. Not your normal human, not a normal human, I'll introduce this human later, but not your normal human, a superhuman. And this particular computer was able to beat it using, in a contest called ImageNet, and I'll talk to you about that in just a moment. It leads to some pretty exciting implications. Amazing year in visual computing. We had a fantastic year. I want to thank all of you guys for that. Now, all of that is just the tip of the iceberg. That's the results. Those are the results. What makes it possible are the work that we do here. Developers who find a computing platform useful to them, developing amazing software on top of that computing platform, which goes off to introduce new ideas, new breakthroughs, new discoveries. It's all because of the work that you do here. That's what GTC is about. GTC is about you. GTC is about developers. Now, if you go back and think about where we started, GTC's first year was 2009. We introduced Tesla. We invented CUDA in the year 2007. I think the GPU, many of you guys would probably still remember, the GeForce 8800 GTX. 8800 is potentially one of the most important GPUs ever created. It spawned off, of course, a whole generation of GPUs, and I'll show you one today. 2 years later, we had our first GTC. And the statistics are interesting. That year, we had 150,000 CUDA downloads. With almost no public awareness, no advertising campaign, 150,000 downloads of CUDA was done so that you can experiment with accelerated computing. There were 27 CUDA apps. There were 60 universities that are now starting to teach CUDA, accelerated computing. And of course, one of the things to realize is that what we enable with accelerated computing is really the world's most popular, world's most accessible supercomputing platform. Any researcher, any student, any engineer can reach out very, very easily and get a GPU that is powered by CUDA and therefore could accelerate their research. 4,000 papers were written after about a year and a half. We shipped a whopping 6,000 GPUs under the brand of Tesla. Now that's in the context of 100 million we ship per year. Out of 100 million, we shipped 6,000, and there were 77 teraflops of GPU accelerated computing in supercomputers. Let's fast forward that just a few years. Now there are 3 million CUDA downloads, 319 CUDA applications, 800 universities around the world. This spans basically the globe. 800 universities around the world now teach CUDA and GPU acceleration. 60,000 papers. 60,000 papers citing the use of GPUs for the research, and 450,000 GPUs now power supercomputers and high-performance computing centers all over the world. And this statistics is absolutely shocking. There are now 54 petabytes of combined high-performance computing power that now powers the globe. Amazing progress in just a few years. I want to thank all of you for that. The promise that we made you, and the promise we fight every day to keep, are several things. One, we promise that by adding a GPU into your platform, and by you making the effort to program that GPU, we will accelerate your code. We will accelerate your code not by a little bit, we will accelerate your code dramatically. Number two, that we seek always to find that fine balance between enhancing your productivity and making it easier and easier to program this platform, enhancing your productivity, while at the same time, never losing sight of that fine, delicate balance between easy to program to use a computer and that computer being incredibly fast. Most of the applications we serve are really about speed. Without the speed, it is simply impossible for you to do your work. One of my favorite quotes, and I sent this to you guys a couple of years ago, was when a researcher came to me and said, Jensen, because of your work, I'm now able to do my life's work in my lifetime. That is what it's all about. We have to find that delicate balance between programmability and speed. And then number 3, access. Any computing architecture worth a salt is really about access. You need to be able to reach out, and any researcher, any student, any developer, anywhere in the world, in any industry, should be able to reach out very easily and find this architecture. One of the things that we're most proud of, and it was a sacrifice we made early on, is put CUDA on every single GPU, long before people found value in it. By making it available on every single GPU, from desktops to laptops to supercomputers to data centers, and now in mobile devices, and now in your cars, by putting CUDA in every single GPU, we make it as easy as possible for you to develop and to deploy your software. And then lastly, of course, the beauty of an architecture, once you develop the software, if your partner is dedicated to advance that architecture day in and day out, without you having to lift your finger again, the investment that you make improves over time all by itself. The power of Moore's Law. And that's what we promised you. And today, I'd like to show you that in every possible way, we're living up to that promise. Ladies and gentlemen, let me introduce our brand new GPU, the Titan X. Roll it, guys. 8 GPU. Ladies and gentlemen, the Titan X. $8 billion transistors. The first chip we designed, the first graphics chip we designed, called the Reba 128, was 4 million transistors. 4 million transistors. A small difference since then. This is 8 billion transistors. The team did just a fantastic job. 3,000 CUDA cores. The highest single precision throughput of any GPU we've ever created. It's designed for single precision. It's designed with a 12 gigabyte frame buffer. And as you will see in just a moment, the reasons why we made such choices. For people who want double precision, we still have Titan Z. Titan Z is still the fastest single card double precision GPU we have. The Titan X is the highest performance single precision, the largest frame buffer, the most advanced GPU architecture ever created. This is all based on Maxwell. Okay, ladies and gentlemen, the Titan X. Now let's take a look at what Titan X can do. This is work that we're about to show you that was done by a company called Epic. Epic is a long-term partner of ours. They're a game engine company. They are the game engine you choose if you're developing a AAA title. Now the animation you're about to see is completely in real time and is running on one Titan X. Everything you're about to see is real time, running on one Titan X. It captures 100 square miles of 3D graphics. Literally 100 square miles of 3D graphics. Basically, the entire Silicon Valley. You're not going to see Silicon Valley, you're going to see something a little bit more beautiful. 100 square miles, 15 million plants. You're going to see 15 million plants. This entire terrain was photometrically scanned because it's impossible for artists to have captured landscape that beautiful, that great. Any given frame is 20 to 30 million polygons. Everything is in HDR. The camera effects are beautiful. You're going to see physically based rendering. The rocks look like rocks. Water looks like water. The shadows are beautiful. You might even notice some rim lighting off the shoulders. This animation, this rendering, real-time graphics, is the most beautiful that I've ever seen. And this is just incredible work by the team at Epic. I love their work, and they've just outdone themselves yet again. Ladies and gentlemen, let's take a look at it. Titan X and Unreal Engine 4. You know, if you take a look at that and you just reflect on the best cinema effects that you've seen over the last 20 years, that rivals it. And that helps you understand where this industry is going and where we are going. It is the case that we will continue to advance the future of computer graphics, make it more beautiful than ever, more wonderful than ever, to the point where stories could be told that way. That story was simply impossible to tell without the advancement of computer graphics. We're so excited by the work. You just take a look at that, it just takes your breath away. I'm amazed by the work. Titan X is more than graphics though. Titan X, because of many of you, many years ago, helped me realize the importance that it could be used in a new field of computer science. Some people call it machine learning, evolved greatly, now it's called deep learning. We're going to talk a lot about that today. But one of the things that we did was focus on this application and continues to advance it. It was discovered in the year probably about 2010, about 5 years ago, maybe even 6 years ago, when some of the work that was done at Google led to some work that was done at Stanford with our engineers and our researchers, discovered that it's possible to put deep learning and these deep neural nets on GPUs. And we discovered that the acceleration of training, which takes utterly months, it takes months to train these very complicated networks with a large amount of data, we could accelerate it dramatically. We were able to achieve in just a week's time what non-accelerated platforms would do in several months at the time. Well, since then, we've all made a lot of progress. Even if you compare it against the highest end CPU with a 16 core, and most researchers don't have 16 cores by their side. If you had a desktop computer, you had 6, maybe 8 cores. But if you had 16 cores, training the now famous AlexNet took 43 days on a CPU. A Titan that we introduced a year and a half ago or so is able to do it in literally a week. From a month and a half down to a week. Now, when you speed something up by a factor of 2, speed something up by a factor of 5, when it took a few milliseconds to do, that's important. But when you speed something up that took a month and a half, and you reduced it down to a week's time, it could be the difference between your willingness, your ability to actually do the work versus not at all. Titan was able to reduce deep learning training to about a week. We then introduced a new middleware called cuDNN. With all of our engineers, we found ways to improve the mapping of these convolution networks onto our GPU's architecture. That middleware is called cuDNN. It's been downloaded thousands of times. One of the most popular middleware that we've ever done. And it reduced it even further. Now, when you think about those charts, the second green dot, the second green bar, relative to the first green bar is really nothing to be that excited about, with the exception of the fact that you saved a day and a half. A day and a half in the life of a researcher. A day and a half. And then finally, with Titan X, we're now able to reduce your turnaround time, your training time, from 43 days to just 3 days. Enormous, enormous speed up. It's utterly, utterly life-changing. And I'm going to show you some other results in just a moment, but that tells you what Titan X's can do, and is the reason why we do it. All of that in your hands, researchers all over the world, $9.99. Now, that's right. For just think about that. $9.99. You'll pay for it in an afternoon. It'll pay for itself in literally an afternoon. Surely it'll pay for itself in a day. The most advanced GPU we've ever created, the fastest GPU we've ever made, 12 gigabytes of frame buffer. Every deep learning scientist is craving for more memory capacity, and Titan X gives you twice as much as what we had earlier. The 980, GTX 980 is now from 6 gigabytes to 12 gigabytes, all for $9.99. So, Titan X. Second announcement, let's now talk about a super fast box. Before I do that, let me give you a quick short summary, short history of deep learning. Now, of course, this is one thread. There are so many threads, and so much work in deep learning was built, obviously, on the work of other giants before it. But there were a couple of very important events that I'm going to highlight today, not because they're the only 2 events, but in the context of my story, those 2 events are the primary threads. It all started, really, in 1995. Well, at Bell Labs, Jan LeCun observed that traditional computer recognition, computer perception, could be done better. There's little edges, combinations of edges. They count the histogram of edges, the density of edges in a particular image. And from those edges, they would infer what object that we're looking at. Most of that work was a patchwork of hand-engineered codes that have been built up and techniques that have been built up over years and years and years. As you know, computer vision has been around for 50, 60 years. Jan's observation was that instead of writing all of these hand-tuned codes, the world is so complicated, there aren't enough engineers to ever write all the code necessary to figure out how to understand the world, how to perceive the world. And he observed that, in fact, there's something else that's growing very quickly. That computation was growing quickly. That Moore's law was moving faster than the number of engineers in the world. Certainly the number of computer vision engineers in the world. And so he came to the conclusion that maybe an approach that would be viable is to create a network, to design a network he called a convolution network, that would be auto-trained. That it would start up with no software. It would start up unprogrammed, inspired a little bit by biology. Most of us were started with no programming. But it would start with a well-engineered neural network. He called it a convolution neural network. And if you had enough data, and more importantly, if you had enough computation, you could train this network and program it to observe and to recognize objects in the world. Well, that was his observation in 1995. He wrote a very, very good paper on that. I recommend everybody reading it. In 1998, he revealed with his colleagues a network that was built using that approach, and it makes sense that Jan would call it the net, otherwise known in English as the net. The net was a deep convolution network. Layers and layers of convolution networks, and each layer would attempt to self-train, to learn through all the data you provided and the enormous amount of computation that you provided. It would learn what programming would detect features of images that it was presented with. The first layer might turn pixels and represent them as edges. The second layer might turn edges and discover what is known as textons, patches of textures. And the next layer after that may build up these things into higher level parts. Maybe the ears of a cat, the eyes of a dog. And then the last few layers, what is known as fully connected layers, would then assemble these pieces and translate an incoming image into a singular number at the output of this neural net. And that number would represent the encoding of a representation of that object. So the dog would have a representation in numbers, a cat would have a representation in number, a car would have a representation in number, and if we train this network to recognize 1,000 things, there would be 1,000 numbers in this vector. Well, that was his invention in 1998. Lynette crushed the best handwriting recognition software up to that time. Utterly crushed it. Lynette is still in use by banks, by the post office, to recognize billions of pieces of handwritten checks and letters, and amazingly is able to recognize numbers and text no matter how bad you're writing. Well, I'm not sure that that's the case, but very bad writing. Somehow it has learned from all of the data that has been presented the ability to recognize numbers and handwriting recognition so reliably that it's now used, completely replacing humans. That was in 1998. Now, of course, a lot of research was done since then. A lot of research has been done without any public notice. These researchers dedicated to artificial intelligence, dedicated to machine learning, dedicated to deep learning, continue to advance the art. And all of a sudden, one day in the year 2012, Jeff Hinton's lab, University of Toronto, young man, Alex Krzyzewski, created a network that I referred to earlier called the AlexNet. The AlexNet entered into a competition, an international competition for large-scale visual recognition, the annual competition, the annual Olympics, if you will, of computer vision, entered into that competition with the AlexNet, created from Hinton's lab in University of Toronto, and it crushed, utterly crushed, the work of computer vision scientists over 50 years in one day. Whereas computer vision was making slow progress and incremental progress, and features and more code and tuning of code, one day Alex Krizhevsky introduces the AlexNet that he trained on GPUs, and it was the only submission based on GPUs that year. And it crushed everything that was there before. 84% accuracy, 16% error. That day was a very important day. On that year, he was the only person, Krizhevsky was the only person that submitted work that was trained on the GPU. The next year after that, 50% of the work was trained on Nvidia GPUs. The year after that, almost every single submission was based on GPU accelerated training. Something happened, and it was very, very big. And in fact, it didn't stop. So it turns out that the event, I think, just happened in September and had an error rate of about 7%. Literally, days later, Baidu, Andrew Ng's lab, announced that they had broken that record at 5.98% of error, or 94% accuracy. And then days after that, Microsoft announced that they were able to, for the very first time in the history of computer vision, beat a human in recognition. Now this contest is this human. Let me tell you about this human. This contest is quite amazing. You have to be trained on 1.5 million images. I mean, first of all, I can't even imagine 1.5 million images. You train on 1.5 million images, and you have to train your neural net, this deep network of yours, to recognize 1,000 things. 1,000 things. Now, it's 1,000 things and many species of dogs and fruit and things like that. I'm not sure I know 1,000 things. But anyways, this network is trained on 1.5 million images, on 1,000 things, and then it has to be compared, of course, to each other, but for the very first time, because the sacrifice of one young man, Andrei Karpathy, he's sitting right there. Maybe, Andrei, just stand up for a second. Let's just pop your head up. Ladies and gentlemen, Andrei Karpathy. One of the great researchers in this field, and a researcher from Stanford, and I'm going to have him talk in just a moment, but he is the reference human. I have to say that not only did he go through extensive training on that database, he is the reference human, which basically says any one of these results would have beaten the rest of us. Okay, this is an amazing achievement. Microsoft, for the very first time in history, a computer was able to recognize images better than a superhuman. And then shortly after that, literally days after that, Google announced that they beat that result. The race is on. The race is on. Now, why did this happen? You know, why did this happen? This is the Big Bang, if you will. The Big Bang of computer perception. The Big Bang of computer perception. And why did it happen now? Well, three things. Of course, the invention of this, if you will, general, unprogrammed, and I will go way too far and say simple approach, and Jan would always say this is the simple design of a network, inspired by biology, something that you can train with an enormous amount of data and a massive amount of computational horsepower. This design made it possible for us to use this network on so many things and for so many people to be involved, because we don't each have to design our little features, if you will, our little hog feature detectors, histogram of gradients, or SIF detectors, and so on and so forth. We can now use this basic design and architecture of a network and use it, literally, to train on almost any data. The second thing, of course, is the emergence of large data. It would have been possible without the internet. The researchers at Stanford, under Fei-Fei Li, worked on this database, the world's first hierarchical database, and it has 15 million images in it with 22,000 categories. And it's all hierarchical, meaning that underneath dogs, there's a whole bunch of species of dogs, and underneath fruit, there's a whole bunch of species of fruit, and underneath, above dogs, probably have mammals. It's completely hierarchical, and it's all labeled. There's still some error, of course, in it, but it's largely labeled correctly. It was largely labeled correctly because of one thing, the emergence of Amazon's Mechanical Turk. I don't know how many people contributed to this work, but obviously a lot, and they all were paid. Fei-Fei tells me that it's 4 cents or so for every image that they somehow tagged. And you could imagine, without the internet, without big data, without all of those cameras, all taking pictures, and these pictures are kind of messy. Lighting conditions not always right, the orientation's not always right, there's a whole bunch of different versions of the same thing. Somehow these 22 million images tagged by humanity off their cameras all contributed to this hierarchical database called ImageNet. Because there's this one standard large database, we now have access to data. All we need now is a supercomputer. And that's our contribution. With the invention of CUDA, with the invention of GPU, and putting it into the hands of literally every researcher in the world, Titan became the platform of choice of deep learning network researchers all around the world. Those three things together, the democratization of supercomputing, if you will, large data, and the invention and the observation of one brilliant scientist in 1995, and then all the contribution of work since then, resulted in the Big Bang, 2012, the Big Bang of computer perception. Let's take a look at this network, shall we? This network is interesting. Inspired by the human brain. It doesn't work like the human brain, it's inspired by it. Whole bunch of neurons. The neurons are modeled as little tiny simple processors. There are 3,000 processors in the Titan X, running, call it, at a gigahertz, at 1 billion cycles per second. These processors are connected with each other, of course, on one large internal fabric, using this idea called shared memory that many of you know about. This network composes of a whole bunch of neurons, little tiny processors, and these neurons are connected to other processors. The connection it has with other processors are weighted, depending on the importance of that connection. There are receptors on the top layer, or excuse me, the bottom layer, as it turns out, which is on your left. Oh, you know what? I thought I was talking to that slide. Mike, can I go back to it real quick? Sure. Okay, there you go. Sorry. Thank you. Now, one of the best things about GTC's keynote is we don't rehearse very much, and people always say, "Hey, Jensen, it always seems so spontaneous." Guess what, guys? Here's the way I think about it. We should be preparing all year, huh? And so this is just game day. Okay, we were preparing all year. And so let's think about this network. On the left-hand side, these are essentially right on the other side of it are basically receptors of your retina. And these things are connected to neurons that apparently detect certain orientations, otherwise known gradients, of these edges. Somehow over the years, these biological things, we recognize edges, a whole bunch of them, and we recognize textures, combination of edges. And so what's amazing about this thing is this network this network starts out with these receptors. In this case, this particular network is AlexNet, has 5 convolution layers, which is represented by the green boxes. And each one of those boxes increases the scale of recognition, if you will. The lowest level, the flattest level, is looking at small features across the entire image. The next level of scale, it might be looking for what I mentioned earlier, textons or patches of textures across a higher scale or a lower resolution of the image. And then after that, it could move up another scale, look for parts, and then so on and so forth. The last few layers, those patches of colors at the end, are what they call fully connected layers, and then assembles these parts, if you will, into a vector, recognizing it as a car, if you present it with a Ferrari 458. And so this network, the convolution neural net, was the invention of Jan LeCun in 1995. Obviously has evolved greatly over the years, but a lot of the basic ideas have retained. Now, Mike is going to give us now, this is Mike Houston, he's going to give us a visualization tutorial of how this network works. Now, what's important to understand is the amount of computation that's within it. Each one of these volumes, if you will, is doing convolutions simultaneously across all of those weights, across all of that image. The simultaneous computation of layers and layers and layers and layers of convolution, which is a mathematic term for testing for a particular patch of filter across an image. Okay? Mike, take it away.
So Jensen said, what you're seeing here is a finally trained version of AlexNet. So the green pieces, again, are the filter banks, these convolution layers that we've built. The red images that you're seeing are actually the activations. And then the images to your far right are the fully connected layers. So let's rotate the network, and let's fly through it mathematically, how this image is being applied through the network to get its final result. So we're going to take our cute little bunny here, and we're going to walk through the network. So we're going to take this bunny image, we're going to apply all these linear filters. These are these edge detection filters that Jensen was describing. They're also known as Gabor filters, and they represent sort of the visual cortex in the human brain. They're a good analog for that. So we multiply each of these filters across the image to get the resulting activations. So there are 96 filters, and so we get 96 activation outputs. And then we take that, and we go through an extra step that's unique to AlexNet. And what this step actually does is it amplifies and selects the dominant features that are then fed into the following network. We're going to continue to apply all the way through these weight networks as we fly through the network until we get to a fully connected layer. So each of these is increasing its abstraction, sort of how deep the feature descriptor is and what its parts look like. And then the first fully connected layer is going to take those parts and begin to mix them together. So if we continue to fly through, and we're going to shift so you can see the output vector here. In this case, this is the output result, this histogram, that high-dimensional vector, 1,000-dimensional vector. So if we take our bunny, this is the output of bunny. So you can see that really strong bar. So it turns out that the classes here of bunnies are grouped together. It's actually an angora, but the network actually understands even subspecies of rabbits. So we can actually look at how that changes as we change other variables. So for example, we put a dog through. As Jensen said, there's lots of species of dogs, so we get a lot of activations, but we get a few in particular. So this is actually a mixed breed, which is why it has a couple of very white, bright bars in it. Does anybody know what that dog was? So it's some type of hound mix.
Ask Andre, he knows.
Andre, do you actually know what dog that is? So, and here's a koala. So the koala is an interesting one because the network actually struggles here. It gets koala as the highest output, but if you look at all the other ones, you get things like squirrel and other types of sort of small mammals. And similarly with a cat, you kind of get a similar sense where it's still grouped sort of in mammals, which is why you still get that sort of histogram chunk there. But again, there's multiple subspecies of cats. So that's taking a fully trained network and going through and seeing how it outputs things. So let's switch and look at actually training a network from scratch.
Now, before you start, remember, this is how the network starts. It's a bunch of random numbers in it, and it's largely unprogrammed. I mean, all that's been done here is that the architecture, which requires some amount of understanding about imaging and such, the architecture of the network was designed by the engineers. The architecture of it was designed. How many layers of the convolution? How many layers of convolution networks before you apply them to the fully connected layers? How wide and how deep are these convolution networks? All of those parameters were somehow engineered somehow by the data scientists. But it starts out not able to recognize anything. Okay, go ahead, Mike.
So we're going to start from a blank slate, as Jensen said, and then what we're going to do is we're going to start pumping lots and lots of images through. We'll push those through the network, and we'll get a result. The result will be wrong. It'll modify that result, and then back propagate, and basically correct all the error through as we go. So if we watch us put in images, what's amazing is how fast those features in the front actually form. Those edge filters form almost instantly, and they maintain fairly stable. So this is an interesting property of these networks. The remaining training actually happens in the much later layers. What's happening as the accuracy increases, the learning rate is decreasing, so the rate of change is also decreasing. So we actually reach the point where the human eye actually can no longer see changes because they're so minute in the network. So as this network goes through, it basically gets smarter and smarter, and then researchers basically keep training until it begins to stabilize all the way out. So if we look at a comparison,
by the way, all of this is being visualized. This volumetric rendering visualization is in itself very complex. This is being visualized on a volumetric renderer we call Index. Index gives you the ability to visualize very, very large scale volumes, such as seismic processing or imaging, medical imaging or such. And we're using it in this particular case to visualize the enormous volume of a neural network.
so this was AlexNet. So for comparison, remember this was just a few years ago. For comparison, let's look at actually one of the winners from last year's. So if we look at the VGG network in comparison, it's a tremendously deep network by comparison. So you can see how big it is. It's a 19-layer deep network. So this improved the accuracy tremendously and shows a big shift. If you remember how big the volumes were in AlexNet, you notice how small these are. They've switched to deeper, sort of narrower volumes. It's actually a very interesting result in modern neural networks. And this is now the basis for most of the current continuing research. Most people use this VGG network, and the accuracy is a significant jump over AlexNet. But you can get the sheer scale of how big these things are now getting.
That's great, thanks a lot, Mike. So Mike just wanted to give you a flair, a sense of what a deep neural net is about. One of the things he mentioned earlier that's really important to realize is that when we trained this network, we showed it an image, and we compared it on the other side of the output of it. Initially, when the network is completely empty, we compared it to what is the right answer. And if it's wrong, we compute some kind of an error function, and we back propagate that through the network, adjusting all of the weights along the way. Okay? And it would do this over and over and over and over again, and that's one of the reasons why it's so computationally intensive. Lots of mathematics involved in the neural net itself, and you've got to do it iterations after iterations after iterations. Now this particular, the Big Bang in 2012 caught so much attention around the world. Anybody who's a data scientist, anybody who's working with unstructured data, anybody who's looking with big data, anybody who's trying to predict the future, predict what's about to happen based on patterns, uncomputationally extracted patterns, impossible to compute patterns that are observed in a large amount of data. People who are doing that, who have those kind of needs, are jumping into deep learning. The number of companies that are involved in deep learning has just exploded. Now this is a partial list, but the important thing is this. The partial list includes everybody. Every internet service provider, every major computing company, the type of applications for deep learning, and to enhance the smartness of our applications, to enhance the greater insight that we can derive from large data, is really craziness. Intelligent video analysis. Surveillance will never be the same. intelligent video tagging, image tagging, recognizing images, image search, voice translation, the universal translator you guys saw earlier. Even companies who are platforms of deep learning, so that other companies who are building smart applications could be bolted on top of their platform. I could just imagine applications like Twitter and Uber and all of these amazing applications, all now powered by deep learning. The recommendation engines of movies and Amazon are just going to go through a whole area, a whole new phase of renaissance. Applications are going to seem smarter than ever, all because of some of this work. And that's why the excitement all over the world. Deep learning is also sweeping the industries and sciences. There are so many researchers whose work has been transformed as a result of this discovery. Turns out that predicting cancer is about understanding the rate of growth of cancer cells. The splitting of cells, mitosis. Now, instead of having a very trained doctor looking at biopsies, you can now use deep learning to analyze the patterns by themselves and do an even better job. Discovery of drugs, designing of drugs, largely is about testing, well, of course, designing the drug, but testing it against the human body and deciding whether this particular design of a drug would be toxic. There are hundreds of thousands of chemicals that could be toxic to humans. How do you possibly take all of the permutations of your drug design and figure out whether it's going to be toxic to a human? Now, the researchers at Johann Kepler's University has been able to figure out a method by which they can use deep learning to predict whether certain types of drug designs without experimentation could be ruled out and determined to be toxic to humans. Groundbreaking, game-changing work was done at the University of Toronto to predict from your human genome whether you're going to have a genetic disease or not. It turns out that we've already sequenced the human genome several years ago, 2003. It was discovered to be, in fact, very, very complicated, some 3 billion codes, if you will. We have 20,000 or so codes, genome codes in the human, tens of thousands, and many of those permutations happen, or combinations of permutations happen, and yet rare diseases show up. Some permutations turn into severe disease like autism. The researchers at the University of Toronto, using deep learning, studied this enormously complicated human genome code and trained it against mutations that leads to a disease, mutations that don't lead to disease. All of their data set goes into this deep neural net and trained it to predict whether certain combinations and certain mutations will lead to a genetic disease. Groundbreaking work. The list just goes on and on and on. And this is just the beginning. This is just the beginning. Deep learning, the deep neural nets, the network designs are evolving. The architectures of the networks are evolving. And in fact, even the combination of networks are evolving. The type of applications, the things that you can teach a network to predict is evolving. The folks at Stanford, led by Fei-Fei Li's Artificial Intelligence Lab and researcher Andre Karpathy, is doing some really, really amazing work. And in fact, we don't, Mr. Human Reference, and I was joking with him earlier, someday, you know, like today, the unit of pressure is Pascal. How many newtons, how many pascals? Someday there'll be how many Andres? Your network, how smart is it? How many Andres is it? Well, it turns out, he said, he told me just days after he was beaten, the best network is now 1.5 Andres. Ladies and gentlemen, let me introduce the Andre itself, Mr. Andre Karpathy. Andre is doing some really amazing work. And one of the works that he's doing is taking a look at extracting combinations, multiple objects out of it, and trying to figure out the relationship of it, and translate basically images to text. Andre, why don't you tell us about your work?
Right. So we have developed a deep learning model that is capable of taking an image and describing it with a sentence. So this model is composed of two neural network modules. So we take a convolutional neural network, which we know can see, and we take a recurrent neural network, which we know is very good at modeling sequences. In this case, sequences of words that make up a sentence. And then we take those two modules, and just as if we were playing with Legos, we join them together to form a single module, a single neural network. And then these two modules, and this is a very natural thing to do, by the way, with neural networks, because all neural network modules speak the same language, the language of vectors of numbers. And so once we join these two modules together, the networks learn how to work together and adjust each other in order to perform best at some end task. In this case, the task of describing images with sentences.
Now, Andre, before you show them your network in action, tell me, what's the network size? How would you describe the network size of the CNN, the network size of the RNA?
Right, there are several ways to quantify that, but we're looking at roughly, so the convolutional network is a VGG network in this case, and the recurrent network is roughly 1/10 of the size in maybe number of connections.
And how did you train this network? What is the data set? Now, of course, the CNN, the VGG network was already pre-trained, and it was pre-trained on basically the ImageNet database.
That's right.
And then the text recognition was probably some kind of a pre-trained network as well?
Right, so all of these neural networks are based on some data. In this case, we need data of images and sentence descriptions. And in this case, again, Amazon Mechanical Turk was used to annotate images with sentence descriptions, and that becomes our training data in order to actually train the recurrent neural network part of it and the connection between the convolutional network and the recurrent network.
And how big was the training set for you?
It's approximately 100,000 images and 500,000 sentences.
And when you trained it, at the time that you trained it, how long ago did you do this anyways?
Right, so the convolutional network takes approximately even 2 weeks or so to train on multiple GPUs, but that is pre-trained. Then the recurrent neural network that we train with convolutional network, that takes on the order of maybe 1 week on the GPU, or it can take several weeks, depending on the size of the model, but certainly multiple days.
Okay, well let's take a look at this and see what it can do.
Right, so here we're going to go through several example images. So in this case, we see an image, and this image goes through the neural network, and the neural network starts to sample words one at a time to describe this image. So in this case, the network thinks that this is a bird perched on the branch of a tree.
Now recognize, everybody, that earlier, when Mike was showing you the demonstration, he demonstrated cat, dog, koala. Now this is, if you would have used the same network, they would have come up bird.
That's right.
They would have come up bird, okay? But it didn't come up with just bird. It says this is a bird perched on a branch of a tree. Now imagine what you would have said. Imagine what you would have said about this particular image. Now let's take a look at a few other images. Okay. What would you say about this image?
Okay. So our network thinks that this is a large airplane sitting on top of a runway.
Not bad, all by itself. Okay, let's take another one. What would you say about this image? Ask yourself what you would say about this image. A man riding a horse-drawn carriage down a street. I know, it just stopped about 90% of us, right? But this is obviously a very good answer. All right, next. What would you guys say about this one? Wait for it. Okay? A boat is docked in a canal with a large building in the background. Pretty darn good. Pretty darn good. What would you guys say about this one? I would have said Photoshop. Okay, now we're starting to push the boundaries of the limits of this network. Obviously, this network doesn't see too many examples of a fish flying. And that's one of the reasons for that. Okay, next. What would you guys say about this one?
Okay.
Now, proportionally, I would say it's not bad. Proportionally, I would say it's not bad. Apparently, Andre, your network's not very good at age.
Right. Yep.
Okay, wait for this one. Guys, what is this? You guys recognize the people? 2 children going down a sled, maybe? 2 politicians, maybe? Terminator, maybe?
So of course the network is not aware of the identities of these people. But
so I think the key point here, Andre, is you have some work to do. All right, you guys, Andre Karpathy. And so as Andre said, one of the greatest challenges right now is teaching the networks. One of the greatest challenges is teaching the networks. And what we like to do is, of course, they're being taught, these networks are being taught in the development of the frameworks, basically the tools, the environments, the networks themselves, and the configurators of these networks. These frameworks are being designed by the best researchers in the world in this field. And there are 3 very popular frameworks. There's the Café framework, the Torch framework, and the Theano framework. These frameworks are incredibly powerful and very good to use, but they're hard to use, and they were designed to be used by the researchers themselves. We would like to democratize. We would like to democratize and make more available these platforms for almost everybody to be able to train networks. And so one of the things that we're going to do is we're going to create essentially a framework of frameworks. This framework of frameworks would be accelerated by GPUs. Not only will it be accelerated by GPUs and will contain all of the best middleware that we have at the time, and all of the investment that you made on top of that, of course, will just continuously improve as we improve the middleware. It will continuously improve as we improve the GPUs. It would be accelerated on one GPU, it would be accelerated on multiple GPUs, it will be accelerated on a GPU that's off on the network, and it will be accelerated over time by the GPU that's in a cloud. Same framework. Same framework. Okay? We call this framework DIGITS. Deep GPU Training System. Deep GPU Training System. It's a deep GPU training system. It's designed for data scientists, and it allows you to train DNNs, deep neural networks. It also allows you to visualize it, so you just test to see if the network is doing what your intuition would suggest that it would be doing, and allows you to manage multiple sessions at one time. The UI is web-based, and so you'll be able to access it from anywhere, and each panel allows, for example, you can process the data, you can configure your network, how deep, how wide, you can monitor its progress, and as I mentioned, you can visualize the work that's going on at this time. Now, in order to package all of this stuff up and make it easy for data scientists all over the world, because right now cobbling all of this stuff together is really, really hard, and you need the deep learning scientists themselves. We've packaged all of this stuff together, created a framework of frameworks, accelerated with GPUs, and now we've also built a single little appliance, we call it the DIGITS Dev Box. The DIGITS Dev Box is a simple little appliance. You take it out of the box, you plug it into the wall, it boots up into Linux, everything is pre-installed. It is the maximum amount of GPU performance that you can get out of a wall socket. You can't squeeze out one more flops. You can't squeeze out any more. We've tested it, it's robust, we've configured it, we changed BIOSes, we tuned the memory. The thermal management system of this box is just designed for you to take it out, plug it in, and know that we've pushed it as far as we can push it. We've tried everything, and this is what we could achieve. Okay? And everything has been tested. It's a nice little appliance. It's got the world's fastest GPU in it. It's got the world's most performance you get out of multiple GPUs. And of course, the framework has been tested with multiple GPUs. The results, we've been sharing it with some friends. We developed it initially for ourselves. And we've now discovered there's a lot of researchers and a lot of developers around the world who desperately would like to have something like this. We've shared it with some people, and the results, early results, have been fantastic. People are just blown away by its performance. Today we're announcing that DIGITS Dev Box. This is a box that we like not to sell in high volumes. And the reason for that is because it was really developed for developers. This is not a product to be used as a gaming box. It's not a product to be used as a general purpose computer. It only comes with Linux. It only comes with these 4 GPUs. It only comes in one configuration. It only comes with no instruction manuals. and all you have to do, but it does come with the contact of a very important friend that you'll have at NVIDIA to work with you to advance your research. And so this isn't something that we hope to sell a whole lot of, but this is something that we built so that researchers like yourself can very, very easily and very, very quickly get up to speed on deep learning and start doing real, meaningful work, which is ultimately your goal. Your goal isn't to do plumbing and be an electrician, to rig these supercomputing boxes for yourself. It's available. You should come to our website. All you do is do a search, or you can come under developers. NVIDIA Digits Dev Box. We're building them one at a time. And this is not a mass production platform, as we mentioned. And so come to the website, fill in the order, let us know why you're going to use it, and then we'll try to prioritize it as quickly as we can. And we should be able to start shipping it in May. $15,000. It's, of course, priced at a level that hopefully all researchers can afford. And like I said, it's not meant to be a business. It's meant to help you. Okay? Digits, Dev Box. But see, that's just the beginning. That's just the beginning. What's really exciting is this. Once you make the investment to engage GPU acceleration, once you make the investment to get onto the train of GPU computing and benefit from what others have benefited from over the years, once you get onto that train, then all of your investment just gets faster and faster and faster. So the question is, how much faster? How much faster? How much more advancement will we make in 1 year? We've been studying deep learning now for some time. We've had the benefit of, because of the researchers in this room, people like Jeff Dean over at Google, Andrew Ng at Baidu, formerly at Stanford, Andre, Alex, all of the researchers that we've worked with over the years. We've learned the challenges of deep learning, and we've applied them to our next generation architecture. Every year, we show you one click out. This year, let me tell you about Pascal. Pascal, of course, a French mathematician, has 3 very important enabling technologies. 3 very important enabling technologies. First of all, it's based on a next generation GPU architecture, so in itself, it will benefit from $1 billion worth of refinement because of R&D over the last 3 years. Just inherently, if it has no more features, it has the benefit of all of the refinements and process advancements and circuit advancements and design advancements. It's just going to be faster. It's just going to be faster. But it has also, on top of that, 3 very important advancements. One of them is called mixed precision. This is the first GPU in our company's history with mixed precision. First high performance GPU, first desktop GPU, first large GPU. Second, 3D memory. 3D memory, getting more bandwidth is easy. Getting more capacity is easy. Getting more capacity and more bandwidth is really hard. Well, with Pascal, we're going to take a big leap forward. And then number 3, this great technology we talked to you about last year called NVLink. The ability to connect multiple GPUs at literally, well, let me just not let that out of the bag, very high speeds, connecting GPUs with each other. Because it's so important now for us to scale the number of GPUs. I just showed you that DevBox has 4. People are asking us for 64. The difference between 4 and 64 is a very big difference. And so a lot of that has to do with interconnect speed. First, just architecturally, without those 3 features, Pascal is twice the floating point performance per unit energy. Big deal already, fantastic. Second, It has 2.7 times the memory capacity, so it's 32 gigabytes instead of 12. Third, it has 4 times the mixed precision performance. A lot of the computation that is done in the convolutional neural nets could be done in lower precisions. FP16 would be pretty fantastic. And so a lot of people are quite excited about this. All of a sudden you get a turbocharge in computational throughput of the convolution layers. However, as you saw in the earlier, the first 5 layers of the deep neural net is computationally intensive. Whole bunch of convolutions, all happening simultaneously as you propagate down the network, up the network. But when you reach the last 3 layers, the fully connected layers, it is just completely, utterly bandwidth limited. And so having 4 times the computational throughput is all good. However, unless you dramatically improve memory bandwidth, all of that could be lost as a result of Handel's law. The last 3 layers could now swarm the computational time of the whole network. And so Pascal has 3 times the memory bandwidth. 2.7 times more capacity, 3 times the memory bandwidth. Now, the question is, what does it all mean? How do I compile it all together? Okay? And so here, I'm about to do what is known at Nvidia as CEO math. It is supreme math. This is a form of math that it's way beyond deep learning math. Way beyond deep learning math. It's called CEO math. And so now I'm going to illustrate it to you. CEO math. Well, Pascal is going to be 10 times faster than Maxwell. Here's how I got there. Notice all the numbers on this slide. There are no decimal points. Done on purpose. Please note, for anybody who's going to be upset if it doesn't turn out to be 10.00, please look at the bottom right-hand corner. These are very rough estimates. Okay? This is utterly for illustration purposes. Now, of course, there are 10,000 engineers at NVIDIA, and they're working really, really hard at every single level of this, from process to circuits to architecture to design to all the middleware, the software, the system, the interconnects, all of that to make this possible. I condensed it all into one slide. All right, so I'm being unfair to so many people that I can't even, but I'm hoping that it could explain why I'm so excited about Pascal. First of all, the forward path. The forward path is the first path or the inference path. This is forward. You do convolution layers, and then you do the fully connected layers, and then it generates a result. If it's a training run, then you compare that result with the right answer, and you compute the delta, the error term, and you back propagate it, and you do stochastic gradient descent, and then you try it again. Okay? So the forward path, and we're talking about learning right now, the forward path benefits 4x from the convolution layers, right? 4x, 2x from just the architecture itself, and then 2x from the mixed precision in FP16, so that's 4x. And then when it hits the fully connected layers, it's 3 times the bandwidth, but we also have FP16 now, which doubles the bandwidth. So it gives you 6x. And then now when you're working backwards, you get back propagation now, and it's 6x because of the bandwidth, and then 4x because of the convolution layer. Well, you know, it's kind of hard to say exactly where, how many convolution layers and as opposed to how many fully connected layers and so on and so forth. And so I just kind of roughly said 5x. It's 5x faster as a result of several things. Mixed precision, well, the Pascal architecture itself, mixed precision, and the benefits of 3D memory that is not just wide, but also very, very large, so that we can keep a large network in one compute node. But it's more than that. One of the things that most people are they're just out of their minds excited about is NVLink. I'm out of my mind excited about it. The reason for that is this. We just simply get enough performance out of the single largest GPU on the planet. Now, just to give you a frame of reference, the box that I just showed is dev kit. The Digits Dev Kit has 4 GPUs, each one's with 7 teraflops, 28 teraflops in 1,300 watts. 28 teraflops in 1,000 watts, 1,300. If you compare that to a supercomputer, in the year 2000, it takes 1 million watts to deliver 1 teraflop. It's 28 times faster than the supercomputer, the fastest supercomputer in the year 2000, and is 1/10 the power. Is 1/10? No, 1,000 times less power. 28 times more computation, 1,000 less times power. Okay? So incredible advancements. Supercomputer next to your box. Well, what we like to do, of course, we could use way more computational capability than that, and NVLink allows you to now scale more GPUs. And the reason for that is because if you're going to split the work across multiple GPUs every so often, you're going to have to update the weights across multiple GPUs. And that is interconnect limited. We now have NVLink, which is 5 times the performance of PCI Express. And if the performance of the computation is 5 times, it says that we can take Digits, which has 4 GPUs today, and convert it and upgrade it to 4 Pascals. However, because we also have mixed mode, mixed precision, we can double the interconnect bandwidth, and as a result, instead of 4 GPUs, the next Digits dev box will likely have 8 GPUs. 8 GPUs. 8 GPUs. And so what that allows people to do, literally, is to train 10 times faster. The training problem is one of the most challenging computational problems today. It is one of the most important computational problems today, and now we can do it 10 times faster. Pascal is 10x that of Maxwell. Let me now change and talk about self-driving cars. Again, in the context of deep learning. Well, self-driving cars have a whole lot of benefits, and we'll talk about it in just a moment. One of its early manifestations is a feature called ADAS. Using various sensors, sometimes using a camera, we can now have driver assistance. Driver assistance basically works by detecting a pedestrian, detecting a car, detecting some lanes, and before you run into the car, before you run into a pedestrian, the car invokes the brakes and stops the car. You could use this basic capability for highway adaptive cruise control. It just follows the car in front of you. If the car in front of you slows down, you slow down. If the car in front of you speeds up, you speed up. And the car in front of you stops, you stop. That basic capability of ADAS is incredibly useful already. However, stopping a car when you detect an object is far from a self-driving car. It's far from a self-driving car. It surely one step. The question is, how do we get to the future of self-driving cars? Now, one next step, of course, is detecting objects. Why don't you just detect free space as well? Detect free space as well. Well, I think that there's a very big difference between detecting an object and doing something and versus understanding the environment, the context of the environment, and figuring out what to do. Driving is not about detecting. Driving is a learned behavior. Driving is not about detecting. Driving is a learned behavior. Our feeling is the right answer is to augment, to add to today's ADAS systems, to augment today's ADAS systems with a deep learning network. That's our vision for the NVIDIA Drive PX. To augment ADAS. Sure, if somebody detects a car, detects a pedestrian, we ought to stop. That feature exists today. It exists in a whole lot of different forms. I think we ought to continue to let it exist. However, we should augment that system with something that will learn the behavior of driving over time. Will learn the behavior of driving over time, and that can be updated over time to become smarter and smarter and better at driving. Now, our perspective of deep learning's impact in self-driving cars is very similar to the perspective to the events that just happened in the year 2012, the Big Bang. I believe the Big Bang of self-driving cars about to come. In the next couple of years, because of the availability of massively parallel supercomputers like Digits DevBox, and the ease of training, the availability of data, just from cameras like GoPro, we're going to be able to train these networks with better and better behavior, smarter and smarter behavior. But we can't do that by coding it with if-then else's. If I detect this before that, and if it's moving at this rate after that, and every single condition, and program a car, and put it on the road, and do it over and over again, you'll never get there. And so we believe that the architecture, just like deep neural nets, the big bang that happened in 2012 is about to happen here in self-driving cars, and it starts by augmenting ADAS with a deep learning network. Now let me just illustrate a couple of things. This particular road here, the easy thing, of course, is to detect that there's a free space in front of you. But that free space, how you think about that free space, in this particular case, I'll just drive through it. That free space changes. The meaning of that free space changes if all of a sudden there's a bus on the other side. And that even changes. If the bus is driving, so be it. But if the bus is stopped and the light is on, my free space all of a sudden recedes quite far. In fact, that free space changes yet again if a car is parked by the side of the road, but the door is slightly open. If that door is slightly open, I know it's about to become fully open, and somebody's likely to step out, and I should be extremely concerned. The free space is now modified. Now, the world of free space, driving doesn't work like this. And of course, here's an example of a free space that otherwise would be a free space. It detects for some anomaly, oil sludge, or maybe it's a hole, or maybe it's a pool of water. For all of us, we would just drive through it. Just drive right over it. If you aim the car properly, it'll just drive right over it. Why stop? Well, the way to think about that is this. How do we think about self-driving, and how do we think about computer code? I think it's going to be very, very difficult to code, write if-then else's, and design feature detectors, and condition detectors, and scenario detectors of an infinite number of possibilities to go figure out how to ultimately lead to a self-driving car. It's a little bit like this. It turns out that ping pong is one of my favorite games. And here's the question. How do you teach a baby how to play ping pong? Well, if we use conventional ADAS methodologies, what we would do is this. First, we teach the baby how to detect a ping pong ball. When it leaves a ping pong paddle, let's go ahead and run that video. How it leaves the ping pong paddle. But that's just the beginning. That's just detecting. This is real.
Yeah.
That's just detecting the ping pong ball. Now here's one way we could do this. We could teach the baby Newtonian physics. When your paddle strikes the ball, depending on the velocity of the paddle, the elasticity of, otherwise known as the sponge, on the paddle, you will calculate the velocity that the ball leaves the paddle, where it bounces on their side of the table, and therefore you do a very, very fast, relatively simple computation. You simulate the trajectory, and before it enters your space, you will start to swing the ball. That's one method of teaching a baby how to play ping pong. Well, this is the way I learned how to play ping pong. I wish I had started then. I'd be smart now. There you go. Here's the way you teach here's the way you teach a world-class athlete how to play ping pong. What you do is this. You show the baby what it means to play ping pong. So you hit a couple of balls, and then very quickly after that, you put a bat in their hands and you let them smack away. And every time it hits it properly, you reinforce the behavior. Every time, if they repeat bad behavior or the wrong way of hitting, after several times, you show it again what it means is right behavior. Well, it turns out that training a baby how to play ping pong and training a car how to drive may be similar. It may be similar. It sounds like lunacy at the moment. Well, it turns out It's not so lunatic. DARPA funded a project called DAVE. DARPA Autonomous Vehicle. The project leaders were two people. One of them I mentioned earlier, serendipitously, is Jan LeCun. Jan and Urs Müller partnered to develop, were funded by DARPA to create a self-driving car, a self-driving vehicle that had no programming at all. There is simply a deep neural net inside Dave. Dave was trained the behavior of driving. Dave was trained the behavior of driving. Dave was trained the behavior of driving. So Jan and Urs is now my chief architect for autonomous driving. Jan and Urs set off to figure out whether that's possible or not. Well, here's Dave in action. Now the important thing about this is this. What Dave is trained to do is navigate in a very hostile environment, and what it's driving over right now is a very hostile environment. It's finding its own path. There's no programming involved. There's, of course, a very well-designed network that's running inside Dave, but somehow it's finding its own way. It's avoiding collisions. It knows what to drive over. It knows what it can't drive over. Some rocks it can drive over, some rocks it can't drive over. The rubber hose is okay to drive over. The wood stick is okay to drive over. But some rocks are too big to drive over, like that wall. And it avoids it all by itself. And it meanders along. And in the size of Dave, he's actually moving pretty fast by that scale. All of this was done on just one CPU. They were very computationally challenged. It was trained on large clusters of CPUs, supercomputers basically. And here's Dave in action. Now it's actually really interesting. This is what Dave was taught with. What Dave was taught was with this. Basically a few 100,000 images, 225,000 images, and it was simply shown an image, and it was also labeled by the human action. What the human did. What the coach did. Shown this image, what did the human do? Shown another image, what did the human do? These are all random objects in the backyard, not the path. This was trained on just some random objects in the backyard, not ultimately the navigation path. You could put it on any navigation path after that. So it's trained by these things. It saw all these various objects, and it was informed by what did the human do? What did the coach do? What is ground truth? What is the right answer? What is the right behavior? It was trained over and over again. Now before it was trained, Dave was not very well informed, runs into that bag. This is trained after 52,000 images. The behavior, the input was images, the output was drive commands. The input was images, the output drive commands. So now it looks at these videos and it does what the human would have done. It looks at these videos, processes it through the deep neural network, and does what the human would have done. And this is fully trained. Isn't that amazing? Deep neural net in action. It is perfect at predicting the expected behavior, the right behavior given a large amount of unstructured data. Deep neural networks are just wonderful at taking large amounts of unstructured data like we do and predicting the right behavior, the best behavior. Now just to compare it to Drive PX. This is what a Drive PX is. So Dave, you guys saw Dave. Dave is basically completely computed on a CPU. This is Drive PX. Okay? Drive PX is 2 Tegra X1s, about 2.3 teraflops. This is a supercomputer right here in this little motherboard. It has 12 cameras that comes into it. So we could feed it with front cameras. In this particular case, Dave had front cameras. We could feed it with cameras all around us. And based on all of the input of the cameras all around us, we could decide by training this network, what is the proper behavior? So the car in front of me stops. However, depending on what I see in my rear view mirror, or what the computer sees in the rear view mirror, and the side mirrors, it might decide the best answer is not to stop. It might decide the best answer is simply change lanes. Okay? There are all kinds of things that we could teach the right behavior. We simply have to provide it with a lot of data. And so this is Drive PX. Now just to compare it to, if Drive PX can process LXNet at 184 frames per second. So the LXNet is that big, huge network that was shown earlier. Drive PX can process LXNet at 180 frames per second. LXNet has, if you can think of it, essentially a brain. This network has 630 million connections. Almost 1 billion connections in this brain. 630 million connections. And we can activate those 630 million connections at 184 frames per second. That's basically 116 billion connections per second. That brain is firing off 100 billion times a second. Comparing what you saw was achievable by Dave, that was 38 million. 3,000 times faster. 3,000 times more neural capacity. So the question is, what can we teach Drive PX to do? Drive PX. Our vision of what this architecture is basically to augment today's ADAS systems. If our little Drive PX, a little drive, starts to veer off into the wrong direction because it wasn't taught properly, or its teaching or its learning is incomplete, all we have to do is stop. The ADAS system will simply kick in. It's no different than us treating our kids. We teach it the proper behavior, we send it off, it gets smarter all the time. However, every so often we tell it, don't do that. That's going to hurt. ADAS system is going to be there for that. To augment today's ADAS system with a deep learning network has enormous potentials. And I'm looking forward to when that happens and the big bang happens in self-driving. All of a sudden, we have amazing cars doing amazing things. And it's constantly getting smarter because we OTA it. Drive PX, our platform for self-driving car computers. It's the most advanced car platform on the planet, car computing platform on the planet. It's available in May as a developer kit, just like Digits, the dev box. We would like you to come to the website, fill out your needs, and we'll get right back to you. The dev kit is $10,000, comes with a ton of software, and it gets you going to build your self-driving cars. Now we could talk about cars forever. And I can't imagine someone who enjoys cars and building cars and building self-driving cars and figuring out where the future of cars is going to go and has broken every rule in building cars and somehow managed to have created just an amazing company. I still remember the first car I bought from him. My only question for Elon at the time was, are you going to be around to service this car if something happened to it? And he says, no, trust me. And look what happened. What an amazing achievement. I have all 3 versions of his cars. It just gets better and better. Not only does it get better and better, each version gets better and better. It just delights me to no end when I get an OTA in the morning. You know, and I read it and, oh wow, all these features. I didn't even pay for it. I'm not suggesting that I'm willing to pay more for it, but ladies and gentlemen, please welcome Tesla CEO and founder, Elon Musk. We made it a point not to rehearse anything, and so I just want to just as a reminder, you're my last thing.
Okay.
Okay. Could you not ruin the whole thing?
All right.
All right. So remember, no, speaking of that, I think everybody would like to, before we get into all of the good stuff, Okay. And they want to go directly to the juicy stuff.
Okay.
Okay, and the juicy stuff is this. Look, you know, you were quoted as saying that artificial intelligence is more dangerous than nuclear weapons.
And I said potentially.
Well, it goes on. It goes on.
It does go on.
You say that it's like summoning the demon.
Could be.
How do you consolidate, rationalize that conflict between artificial intelligence, of course, deep learning, that obviously is going to be very important to self-driving cars? How do you think through that?
Well, I don't think we have to worry about autonomous cars, because that's sort of like a narrow form of AI. And it's not something that I think is very difficult, actually. I think to do autonomous driving to a degree that's much safer than a person is much easier than people think.
Yeah.
I think it's going to just become normal. Like it'll be like an elevator. Like they used to have elevator operators, and then we developed some simple circuitry to have elevators just automatically come to the floor that you're at, and you can just press the button. Nobody needs to operate the elevator. The car is just going to be like that.
And the elevators these days are even smarter. I mean, it knows where to position an elevator, so that if you were to need an elevator, it's pretty close to you. Cars in the future will be pretty smart about that too.
Yeah, you'll be able to tell your car, like, take me home, go here, go there, anything, and it'll just do it. And at an order of magnitude safer than a person. In fact, in the distant future, I think it's probably going to be, if people may outlaw driving cars because it's too dangerous. Like you can't have a person driving a 2-ton death machine.
Now, if we have the right type of intelligence in a car, we also don't have to make the cars that heavy, I would think. You know, cars are getting heavier and heavier, and it's got more and more stuff in it because it needs to survive all these incredible collisions and things like that. And I wonder if we were to design cars that just simply don't collide as much. I wonder if we could relax on some of those laws and make cars more fuel efficient and lighter and better to drive.
You could definitely do that. If you could count on not having an accident, then you can get rid of a huge amount of the crash structure and the airbags. We're a long way from that because there's always going to be for a very long time there'll be some amount of legacy cars on the road. And I think it is important to just appreciate the size of the automotive industrial base. Like, it's not as though, like, when somebody makes an autonomous car that suddenly all the cars will be autonomous. It's like there's 2 billion of them. Okay, so the total number of cars and trucks on the road is 2 billion and climbing. The capacity of car and truck production is about 100 million a year. So if tomorrow all cars were autonomous, it would take 20 years to replace the fleet, assuming the fleet stayed the same size. Arguably, it could get smaller if things are autonomous. But still, it's still, maybe 15 years or something. And it's not all going to transition immediately. It'll take quite a while. So, and it's the same for electrification of cars. Changing that industrial base to be electric, I mean, if all cars were suddenly, if all cars produced were electric tomorrow, it would still take 20 years to replace the fleet. And right now it's less than 1%. So.
Now you mentioned just now about self-driving cars being easier than people think. Now you have your vision of how to go from where we are today. Now my P85D has lane detection, and so it gets a little, when I get close to a lane. Yep. It detects the speed signs, and it uses computer vision technology to do that. And that's today's ADAS. What is your roadmap? How is that different than other people's roadmap? How do you think about how to get to self-driving cars?
Yeah, well, you kind of need the hardware foundation, the sort of sensor and computing foundation, and then you can keep uploading new software. At least you can with a Tesla because it's always connected. So the car that you have, you'll notice like the features are steadily improving. And we now have active cruise control. So it'll use radar and camera fusion to track the car in front of you. It's also looking at with some of the things that are coming out. It looks at the brake lights, so it anticipates that the brake lights are active. It's going to get basically smarter and smarter, even with the current hardware suite. So the current hardware suite is 360-degree ultrasonic sensors that go up to about just over 5 meters. It's a forward camera and a forward radar. So we'll make even with just that sensor suite, we can actually make huge progress in autonomy. We can certainly make the car steer itself on a freeway. We can do lane changes. It's really, autonomy is about what level of reliability and safety do you want. Even with the current sensor suite, we could make the car go fully autonomous, but not to a level of reliability that would be safe in, say, a complex urban environment at 30 miles an hour where the lane markings aren't there and children could be playing and things could be coming at you from the side. So in order to solve that, you need a bigger sensor suite and you need more computing power. And I think what you're doing actually with the Tigers in the future is super interesting and will really be a big enabler for autonomous driving. So I think Nvidia is doing really great stuff on that front.
I appreciate that.
Yeah.
And so some of the challenges that you see, what are some of the technological hurdles that, and there's all kinds of researchers in the room, there are all kinds of engineers in the room. What are some of the technological hurdles that you think are really important for us to go tackle? Surely we're going to get to some better cruise controls on highways. But beyond that, what are some of the things that you would like us to go focus on to tackle for the car industry?
Well, where it gets tricky is just is that sort of urban environment around 30 or 40 miles an hour. So like right now, it's fairly easy to deal with, say, things that are sub 5 to 10 miles an hour because we can do that with the ultrasonics. We just make sure it doesn't hit anything.
Right.
Because you can always.
Which is the right thing to do, Lars.
Just why would you want to hit anything with your car?
Exactly.
So at 5 to 10 miles an hour, you can stop within the range of the ultrasonics. And then from, let's say, 10 miles an hour to, call it sort of 50 miles an hour, that area in complex suburban environments, that's where you can get a lot of unexpected things happening. Like let's say there's a road closure or a manhole cover up and children playing is a big issue, bicycles. Once you get above 50 miles an hour and you're in kind of a freeway environment, then it also gets easier again. Like the set of possibilities is much reduced. So highway cruise is easy, low speed is easy, intermediate is hard. And so being able to recognize what you're seeing and make the right decision in the suburban environment in that 10 miles an hour to 50 mile an hour zone is the challenging portion. But I really think I almost, this may sound a little complacent, but I almost view it as like a solved problem. Like we know exactly what to do and we'll be there in a few years.
Right. Just like Mars.
Mars is not quite as solved.
That's kind of the spirit of innovators. I mean, in a lot of ways, in your mind, you kind of see things solvable, or arguably solved, and a lot of it is really about getting there.
Yeah, we'll take autonomous cars for granted in quite a short period of time. It's amazing how comfortable you get and how quickly you get comfortable with it.
Now, what about government policies? Like, one of the things that I would like to do is I would just like to keep working on my email as I'm driving to work.
Sure.
You know, there's a...
Some people do that already.
Like I said, I would like to do it without breaking the law.
Yes.
So where do you think government intervention falls in some of this stuff? Because obviously, if your car drives by itself and it does it even better than people, you would like it to drive by itself, but largely the laws don't allow you to do that today.
Right, absolutely.
So how do we cross that bridge, and how do you think about government intervention regulations?
Right, so I think it'll from the point at which a car is definitely safer than a person, there's probably at least another 2 or 3 years after that before regulators will allow that to be the case, because they will want to see a large amount of statistical proof that it's not merely as safe as a person, but much safer. So I think what you can do is you can run it in shadow mode, and essentially say, okay, this is what the computer would have done in all these circumstances, and was there a crash or was there not? Like, what are the false positives, false negatives? And then, it's achieve a large population group, and then make a really clear statistical argument with the regulators, and then they're going to digest that, observe it for a while, see if they agree with it, and then I think they will, because the evidence will be overwhelming.
Yeah, and the evidence is actually already quite overwhelming. That if you would have noticed a brake light in front of you in the highway and you didn't crash into a rear-end collision,
right.
A lot of lives are saved. You know, ideally, hopefully, people don't overreact with this unknown technology and prematurely regulate. No premature regulations.
Well, I mean, regulators are... I think when it comes to public safety, I think there's an argument for being quite cautious and making sure that things are okay before there's a change. I mean, I don't think it's the case that right now there's a fully autonomous system and regulators are not approving it. That could really be a substitute for people, but there will be in a few years.
Now, as we get more computerized technology into these cars, and this car becomes really a software-defined car. I mean, a lot of your engineers are software engineers. I mean, that's
absolutely.
One of the great things about Tesla. You guys, right here in Silicon Valley, you're rich with software engineers, and you've got computer sensibility about architecting a computer properly, designing the software properly, designing the software for many generations of cars so it refines, it gets better and better. And it has been getting better. I mean, the software from the first time you sent me my Tesla to the now, it's just like, it's unrecognizable software.
Right, big improvements. I mean, that's why the first thing we try to do is establish the hardware platform, make sure that we have the sensors and compute power. And so we do that first, even though the software is only taking advantage of a small percentage of the sensors and compute power. And then we do continuous updates to make the car more and more capable. And we're going to see a lot of that happen later this year. If I didn't have an announcement on Thursday morning, I would be saying a lot more. But
the audience doesn't understand why they have to wait until Thursday morning. You tweeted it already. You're announcing you're going to do an OTA. What kind of announcement is that? I'm going to do an OTA on Thursday. That's like a new product announcement these days.
It's just saying that there's going to be a call on Thursday morning, and I'll describe what's going to be in version 6.2 for anyone who's interested.
That's so awesome, though. I'm interested. I get excited every time I get an OTA. And it's one of the things that was really interesting is, in the beginning, when we first built the first Tesla together, the Tegra in it, we thought was more than enough. And recently you said, can we just squeeze more performance out of that platform? And it just happened in literally 2 years. Several versions of your software updates, all of a sudden the computing platform is not powerful enough. And it's because you want to add more features, and a lot of features these days are based on software.
True.
Yeah. And so one last question, and it has to do with, I guess, something that a lot of people are very concerned about, which is your car becomes a software platform, and software platforms get hacked. How do you think about that? How do you think about security, and what are some of the things that we could do to try to make the car more resilient to security attacks?
Yeah, I think that becomes really important when the cars are fully autonomous. I mean, the way the cars work right now, every system in the car, it's assumed, could actually have a mechanical failure of some kind, or a logic failure, a fundamental logic failure. So you can always overwhelm the braking of the car with your foot, and you can overwhelm the steering wheel with your hands. So, but when there isn't a steering wheel, or there isn't, a brake pedal or something like, many years from now, then it's really dangerous. But even as it is right now, what we spend most of our time on is making sure that it's very difficult to do a multi-car hack. Like, if you have direct access to a car, just like if you've got direct access to a computer, or even a conventional car, you can do a lot of things to it. But that's less of a concern than somebody being able to hack an arbitrary car or multiple cars. So that's what we focus our energy on, is making sure that in that way, it's a lot like a cell phone or a laptop. You focus on making sure that they can't, or that it's very difficult for there to be any kind of system-wide hack. So we put a lot of effort into that. We have third parties try to attack it. And then certain parts of the car at the very fundamental level, like the drive unit controller or the steering controller, have an additional level of security. So somebody may be able to hack something that's cosmetic, but it's much harder to hack something that's actually physically dangerous. There's multiple levels of security.
Yeah, and so this way, if you were able to penetrate maybe the infotainment system, it doesn't allow you quickly as a result of that.
Right. I mean, it may display a funny message or something, but you would not be able to then control the steering or the motor.
Yeah. Well, the future of cars is so exciting, and the work that you guys are doing are so exciting, and it's great to see you guys pioneering these computerized cars. I mean, a lot of people think about Tesla as the electric car, but I think it's obviously more than that. It's an electric car, but it's a whole computer platform on top of that.
Yeah, I think Tesla's sort of the leader in electric cars, but I think we'll also sort of be the leader in autonomous cars, at least autonomous cars that people can buy. I mean, if there's anybody who's interested in working on autonomous cars, we'd love to have you work at Tesla, by the way. So we're going to put a lot of effort into autonomous driving, because it's just going to be the default thing, and it can save a lot of lives. Yeah, so it'll save a lot of lives, and hopefully one of these days it would be nice if Nvidia's campus has no parking lot. Yeah. Right, it drops us off and then meanders off to a place where the line's a little cheaper, and and parks a whole bunch of cars there, and when it's time to go home, we summon it to come. It will be extremely transformative, that's for sure. But yeah, I mean, when it comes to AI, I'm not really worried about sort of narrow AI like autonomous cars or like a smart air conditioning unit at the house or something. It's more like sort of the deep intelligence stuff that is where we need to be cautious. I actually think there's many potential flavors of AI, and it's odd that we're so close to the advent of AI. Like it seems strange that we're alive at this time. Well, come back every year. Come back every year, and you'll see the work that this group is going to do. I mean, there's so much deep learning work being done here. You have a lot of engineers here as well, and it's fantastic to see the whole community focused on advancing this field. And along the way, we're going to spin off a whole bunch of new capabilities, as you know, that's going to make cars just safer and more fun to drive. Long before we have to get to essentially a self-driving car. There's going to be a lot of versions along the way that's just going to bring joy to a lot of people. Yeah, absolutely. I just hope there's something left for us humans to do. Well, I'm not going to let go of my steering wheel. I've got mine on the craziness mode and the sport steering mode. Is that the way you have it? I mean, you get driven to work now. No, I you have it. I always have it in insane mode. Yeah. All right, Elon, thank you. All right. Elon Musk. Okay, let me summarize very quickly. We announced 4 things today. We had a really exciting show, really exciting event. A lot of it's going to focus on deep learning. You guys know why now. Deep learning is so important. Deep learning is so important to us. And the tools that we're going to create so that we can create the future together. First, I announced Titan X, the world's fastest GPU. I announced Digits DevBots, a GPU deep learning platform so that data scientists could plug it in, get right to work. Pascal is going to be 10 times faster than Maxwell in deep learning as a result of 3 fundamental technologies on top of the Pascal architecture. 3D memory, mixed mode precision, and NVLink. Those 3 capabilities on top of the Pascal architecture will give us a 10x boost. And then I talked about the Nvidia Drive PX, a developer's platform that enjoys the ability to bring deep learning to augment today's ADAS and start us down the journey of creating more exciting cars in the future. A deep learning platform for self-driving cars. Everybody have a great GTC. Thank you.
gentlemen, thank you for joining.